One of the most important things we do in math is build models to solve problems. And a model can take the form of a formula, and the formula might be given to us for a particular kind of problem, or we might develop the formula ourselves from some information about our problem. One of the most interesting ways, I think, though, to build a model is from raw information. And the information may come to us from a lot of sources. It might come from the internet, for example. It might come from some kind of research. In a business, it just might be historical in nature about relationships between variables within the business. Now, if we get information in that form, then that information can often be put into ordered pair form, and the ordered pair is plotted as points. And then once you have the points plotted, and let's say that we have, just as an illustration, I'm using 4 points here. This point, this point, this point, this point, the coordinates are given. Now, the idea for building a model from this information is to find a graph which best fits this information. Now, that graph kind of looks like, for this group of dots, the graph would be a linear model. It would be a straight line. Now, for other information, the dots may form a different kind of pattern. The pattern might be something like this, you see, and therefore the model might be quadratic in nature that we're looking for. Well, let's stick with the idea of a linear model just for the time being, and let's think about the best fitting line for this information. Now, I can move this line around just a little bit. Somebody might think, well, gee, maybe it ought to go through like this. Maybe it ought to go through like that. Maybe it ought to go through like this. Gee, we don't know quite the slope of that line. We kind of know that if it fits the information best, it's going to be kind of between this high point and this low point over here. And it is important to know that the line, the best fitting line, doesn't have to go through any data point. Well, let's go through a process, just kind of a logical thought pattern of how we might develop or investigate for a best fitting line. Let's suppose here, just to begin with, and later on, by the way, I'm going to show you a technique for finding the best fitting line, the equation of the best fitting line. And we're going to even let the calculator do most of the calculations once we take a look at it algebraically. But for the time being, let's just say that one person might come up with the idea that the best fitting line is y subscript 1 equals 3/7 x plus 2. Now notice this is slope-intercept form. So in this model, the slope is 3/7 and the intercept is at 2. And I just picked an intercept of 2 because it's easy. That's all. And then somebody else might say, well, no, I don't think it should be like this. I think that slope should be a little steeper. I think it ought to be something like this. I think it ought to be 5/9 x plus 2. You see, these are two plausible ideas for a best fitting line. Now, how do we investigate for which one fits best? Well, the one that fits best is the one that is closest to the data points. Closest to. So can we not then measure the distance between a given point and each of these candidates for the better fitting line? You see, this distance, we can measure that distance, we can measure the distance here, gee, that one's about right on it, and then the distance to that other one, and just find the sum of those distances. Oh, but wait a second, a distance above these lines would be a positive value, and a distance below would be negative. So they would tend to offset one another. And to make all of the distances positive, what we might do in the calculation process is just square them. And if we square them, then the values are all positive, and we can make a comparison that way. Okay, so we're going to take those distances and we're going to square them. And we're going to add those squared distances. Okay. Now, how do we get those distances? How do we get the distance from here to there? Well, this distance, the distance to to a point on either one of these lines, is f of, let's see, 1, 2, 3, 4. It's f of 4, you see, in each of these functions. So, and then all we need to do is take the difference in the 5 here and the f of the 4 for each of them. You see, to find those difference in y values. Now, let's go through and kind of set it up or organize it in a way that seems plausible. And we know that we're going to find the difference in y components, and we know we're going to square those differences, and we want the sum of the squares to be the least amount. All right, let's go through that process. All right, the actual points are the point 2, 3, 4, 5, 6, 4, 9, 6. Okay, in the y sub 1 function, that's the lower graph here. If I find, if I use this x and find for this function f of 2, I find it to be 2 and 6/7. And then I take the difference between these two. It's 3 minus 2 and 6/7. Oh, that's 1/7. And then I square that amount. Oh, that's 1/49. Okay, so that's the idea. That's the routine that we're going through for all of these. So for the point 4, 5, I find f of 4 in that function. It turns out to be this. 5 minus 3 and 5/7. 1 and 2/7. Square it, I get this. You see, that's the idea. All right, some of these values, a couple of them down here, are going to be negative. All right, that's fine. Now, squaring those, and I want the sum of these squared differences. So I just add all of these. It's 99 over 49, or 2 and 1 over 49. Okay, now I have kind of a reference. I have quantified the fit. You see, I've put a quantity measurement on the goodness of fit for the y sub 1 line. And I can compare that with the goodness of fit to any other line. For example, I can compare it to the y sub 2 line. So we go through the process again for y sub 2. And here are our actual points, and f of each of these x's for the y2 graph, the y2 function, would be these values. And then we take the differences, difference, square those differences, we get this, add them, we find the sum of squared differences to be 3 and 32 over 81. So those sum of squared differences here is bigger than for the y1 equation, and so the y1 equation turns out to be a better fit. Now, if we can make this comparison, I wonder if we can't come up with some way, some formula to generate the equation of the best fitting line. And that's what this is all about. And that equation is called a regression equation. It is a least squares regression. Least squares comes from this sum of squared differences, you see. We want the smallest sum of squared differences for all of the possible models that go through these data points, for all possible ones. Now, how do we make that calculation? Well, it turns out that the calculation is used, or is calculated, or the formula for it is generated by using some of the techniques that we've talked about, partial derivatives and that kind of thing. But as it is simplified, it comes down to this kind of thing. Now, this is not exactly a simple form, but for a linear model in the form y equals ax plus b, we're trying to find the value for a and for b. And it turns out that a can be found by utilizing this formula. Looks extremely complicated, but let me tell you what all of this means. The n is the number of data points that we have. We had 4 of them over here. All right, this is summation notation. It's the sum as I runs from 1 to n of x subscript I, y subscript I. Now, the I is just a counting mechanism. It goes from 1 to 4 in this case. So this would be x subscript 1 times y subscript 1. Oh, that's just the multiplication of the first xy pair. You see, and then you add the product of the next xy pair, and then the product of the next xy pair, and so on. So we would have 4 products here that would be added in order to get this complete sum, and then we multiply times 4. Now, all of this is for no apparent reason right now. This, remember, is synthesized from something else. So we don't know why this is the case here, but we're just trying to apply the formula, and we just want to know what it means before we apply it. Now, here again, we have this summation idea as I runs from 1 to n, and in our situation, as I is running from 1 to 4. so it's the sum of x values. So it's x takes on, this could be x subscript 1, x subscript 2, x subscript 3, x subscript 4. You see, we're just adding the x values, you see, from the table. And then here we're adding the y values. That's all it means. So we're taking the sum of x values and we're multiplying times the sum of the y values. All right? And in the denominator we have n, in our case it's 4, and again a summation, and it's the x subscript I squared. Now, it's the sum of each of these x values squared, and you do the squaring before you take the sum. That is, it's not the sum of x's all squared, it's the sum of x squares. You see, that's really important to realize. Over here, on the other hand, we have minus the sum of all those x values squared. You see, a different kind of thing. Now, there doesn't seem to be any rhyme or reason for this, but let's follow through with it. We would have n replaced with 4. Now, it's the sum of these products of xy pairs. So it is, remember, we had our first pair was 2, 3. Well, it's 2 times 3. The next pair was 4, 5. Well, it's 4 times 5 for this pattern. Then 6 times 4, then 9 times 6. Then minus, and here we have, let's see, the sum of all of those x values. You add the 2 and the 4 and the 6 and the 9, you get 21. Times the sum of the y values. You add those 4 and you get 18. And I'm kind of belaboring this a little bit because I want you to realize that we can follow this formula in order to make the calculation. Even though we're not going to do it very often, we want to be able to do it once or twice, and then we're going to let the calculator do most of the work in just a little bit. But now, down in the denominator, we have n is 4, and then the sum of those x's which are squared. So we have the first x squared, the next x squared, the next x squared, and so on. Sum of those x's squared. And then minus the sum of all of those x's, the sum of all of those x's squared. And here we go with the calculations. We have, for this part, it's 416, and minus that product over there is 378. In the denominator, all of this becomes 548, and all of that becomes 441. Then we collect a numerator and denominator and divide, and we find the value to be 0.355. What have we calculated? We've calculated an approximation for A, the coefficient of x, the slope. The slope. Wow. How does this compare with the slopes that we were using over there for y1 and y2? Well, we would have to calculate the 3/7 and the 5/9. 3/7 is about 0.43. So that's fairly close to this, and 5/9 is 0.56. Well, this is a gentler slope than both of those two. I wonder why. Well, let's see. Let's look at the y-intercept. You see, we haven't calculated b yet. B has its own formula. The formula for b includes the value that we found for a. So it's really important that we get the a value right if we intend to get this right. So b is 1 over n times this summation minus a times this summation. And it's not as complicated as the one before. Let's go through it. We have 1 over n is 4. So we have the sum, as I runs from 1 to n, of the y values. Sum of the y values. Oh, that's 18, you see. And then here, minus a, and we found it to be approximated by this number. And it was just a long decimal, and I rounded it to 3 digits to the right of the decimal point. Sum of those x values, 21. And now multiplying and so forth, we find the b value to be approximately 2.64. Now, this is a little higher on the graph. Remember, our y-intercept was at 2. So the nature of this graph is that it's a little higher at the y-intercept, and the slope is a little gentler. And this then turns out to be the very best fitting line. And here's the model, the general model, and we have found specifically that the a value is this and the b value is approximately that. Let's step through the process of finding the regression equation on the calculator. The first thing we need to do is enter the information, and we do that by pressing the button marked Stat. And here's the menu that comes up. We want to edit, and the icon is on Edit at this point, so we press Enter, and we see some columns. And at the top of the columns, the marks L1, L2 for List 1, List 2, and so on. Now, I can cursor about here, and if I wanted to clear this column, by the way, if you have something on board already, you can press clear at this point and clear the entire column at one time. But notice that I've already entered the information, the 0.23, the 0.45, the 0.64, and so on. And when you enter these, it's a little easier to enter them by entering all of the first coordinates first. That is, enter all of the items in this column, and then go over to the other column and then enter all of these items. At any rate, with the coordinates on board, we would like to see a stat plot. We'd like to see a graph of just the points given by these coordinates. And to do that, we press second and then y equals. Now, second and y equals will give us the stat plot menu. And we just like to turn a plot on, and the cursor is already at number 1. Now I'm moving it down so you can see it, but it was already up here, and if I press enter, then I can make a number of selections. And what I really want to do here is just turn the plot on. Now some other items in the list are the type of plot. We want a stat plot, which is this item. The X list is in L1, the Y list in L2. These are the default settings, and the mark that's going to be made on the graph is this. Now we'd like to construct the graph, and we can use standard settings if we want to, but the calculator can make a rather remarkable calculation about the window. If we press zoom and then cursor down to, oops, I went a little too far, to zoom stat, press that, and notice here are the points already plotted for us. Okay, now we can kind of decide that maybe the linear model is the best model for this information. You see, and if we had a curved configuration, we might want to choose a quadratic model or some other model. But at any rate, now we go to an area where the calculator will make the calculation for the regression equation. And that's found in, let's see, I think it's stat, and then cursor to the right one for the calc menu. And beginning about right here at line number 4, the regression models start. This is a linear regression in the form AX plus B, which is what we want. We're going to select this in just a second. But let me cursor down and let you see the others, and you can probably see it just as easily on your calculator. But this is a quadratic regression, a cubic regression, a quartic regression, 4th degree, you see, and then a linear regression in the form A plus BX, and a natural logarithm regression, and so on. We have other, this one is exponential, this is power, this is logistic, and a sine regression, and so on. So there are many regression models that the calculator is capable of generating for us. Well, we'd like this linear regression. I'm going to press enter and then enter again, and the calculator is making the calculation. Notice the value for A and B are the values that we found just a few moments ago. Now we'd like to construct the equation involving these, this coefficient and the constant, and we can actually make the calculator enter the information for us. You know, it would be possible for us to write the value of A on a piece of paper and write the value of B on a piece of paper and then go over to y equals and enter the information in the form of the equation. But the calculator does it automatically, and we begin that process by pressing y equals, and with the icon blinking to the right of one of these equal signs, we go into the stat menu, and then, now let me see, I may have this, I have to fish for this sometimes. Oh no, it's not here. It's in the menu marked VARs. And pressing VARs, you get this menu, and cursoring down to statistics, press enter, and we want an equation, so I'm cursoring to the right, and we want this top item, the regression equation, so I'm pressing enter, and notice that the equation in a very accurate form is already entered for us. And now we press graph, and the graph comes up, and we see that it does indeed go through the middle of the data points, and that's exactly what we would expect. Let's go through the process again using a real-life situation. Here's a chart of information having to do with years and the number of daily morning newspapers in the United States. In the year 1989, there were 530. morning newspapers in the United States. In 1990, there were 559. In 1991, 567, and so on. Now, with this information, which appears in ordered pairs, now notice that it goes from 1989 and for every year all the way down to 1999. All right, with these paired values here, we could plot these points. And after plotting these points, we could notice the kind of pattern that emerges. And then we could go through a regression model, or we could develop a regression model that best fits the information. We're going to go through that. One thing I want to point out to you is this, though, that for these first coordinates, for these x values, rather than use these great big numbers for the years 1989, what you can do, and by the way, you might not want to use these big numbers because it throws you way down the x-axis, doesn't it? And to avoid that and to make things a little bit simpler for information entry on the calculator, you might just pick a convenient number as a basis year and then kind of go off of that basis number. A good one here is the year 1990. You might let 1990 correspond with a value 0. And then everything else is kind of based upon that. 1989 is 1 year before this, so -1 would correspond with 1989. And then the other years correspond nicely with the last digit, you see. And now we can use these as the first coordinates for those y values. And let's do that. And this would continue all the way down to where we would have a 9. But let's take a look at this on the calculator. The information is entered by pressing Stat and then Enter because we want to edit. And notice that I've already entered the ordered pairs. Just as a reminder, if you need to clear a column, just go up here with the icon at the top and press Clear and then Enter, and all of the values in that column will go away automatically. Now, to see the stat plot, we press second and then y equals for stat plot. The stat plot is already on, so that's okay. We don't need to turn it on here. We would like to take a look at it, though, in an appropriate window, and to cause the calculator to make the window settings automatically, we press Zoom and then cursor down to Zoom Stat, item number 9. Press Enter, and here is our stat plot. Now we observe the stat plot and we decide on the kind of model that we're after, and we have what looks like kind of a linear configuration here. We might think, well, gee, it's starting to curve right here. Maybe we'll use a quadratic model for this problem. Either way, we're going to get a pretty good fit. But let's use the quadratic model in this circumstance. I press Stat, and then I'd like to calculate, so I press the right arrow button one time, and I go down to the quadratic model, and boom, press Enter, and then Enter again, and the calculator makes the calculation for the A, B, and C in our quadratic model. Now let's make the calculator enter the equation automatically, pressing y equals, and with the icon blinking to the right of an equal sign, we press VARS, and then item number 5. We can either press 5 or cursor down to it and press Enter. And then right arrow twice for equation. We want the top item, regression equation, pressing Enter. The equation is on board. Pressing Graph, we can see how the graph overlays the information. It appears to be a very good fit. Now, what do we do with this? Well, the graph allows us to sort of extrapolate or find information which is not within this data set. For example, we can find the projected number of newspapers in the United States in some future year. Now, how do we do that? Well, let's see. Now, we can press Trace right now, and we can jump onto the various data points. Now, notice that I'm doing that here. Right? It just jumps from one data point to the other, and we can verify that our data points are correct by doing this. If I press the up or down arrow button, it jumps onto the graph. And now I'm on the graph, and I can cursor left or right on the graph. Now remember that the value of x corresponds with a year, and this is some number of years from 1990. Remember, the year 0 corresponded with 1990. And so this is 4.5 years after 1990, and it corresponds with this many newspapers. Actually, we want probably integer values here. Now, how do we arrive at integer values? That's maybe the key here. Well, to do that, we need some friendly settings, and to find friendly settings, we might look up here and see where we are with our x minimum and maximum. Now, remember that 9.4 is kind of a magic number for us, and multiples of 9.4. So I might select something that, let's see, this total distance from -2 to 10 is 12. So, gee, the next sort of magic number after 9.4, doubling 9.4, oh, that's 18.8. So let me try for that now if the x minimum is -2 for a total horizontal distance of 18.8, I'll set this up as 16.8. And let's see what happens. I'm going to graph, and the graph comes up just about as it was before. And now let's see what happens when I trace. Now I'm on the, notice at the top it's telling me that I'm on data points, you see, and when I press the down arrow key or the up arrow key, I go on to the equation. And now I do indeed have friendly values. Notice here's 8. Now that corresponds with 1998. And if I want some future year, some year beyond the data points, you remember it went up to 1999, a value of 10 would correspond with, here, the value of 10 would correspond to the year 2000. And let's go to some future year. Let's go to maybe, oh, I don't know, 15 or 20 or something like that. But the idea of going to like a number like 16 would be 16 years beyond 1990. And that would be the year 2006. And we would project then that, or just predict that the number of newspapers in the United States in that year is 863 approximately.